All right, so span extraction, surprisingly amazing, state-of-the-art, bunch of things. And somewhat also kind of interesting is that now that we can have all of these tasks as span extraction, we can unify all of these. And what's cool is that we actually saw improvements in state-of-the-art numbers for a couple of different data sets, especially when you have restricted training examples, where you restrict yourself, for instance, on just 1,000 training examples of sentiment, for instance, then this span extraction BERT will actually give you these state-of-the-art like numbers. So I think especially as a couple of people here work on low resource languages, if you have these kind of unified frameworks and they can deal with a lot of different languages or different tasks, then you can get much better performance. All right, and yeah, again, don't want to go into too many details, but what's most amazing here is these are numbers down here are actually multitask models. So where you can basically have a single model that can do well across all of these different tasks and actually get state-of-the-art performance with the span extraction stuff. All right, now in the last 5-10 minutes or so, I want to get quickly on some of the interpretability and common sense reasoning work that we've recently done and had a bunch of press about. And that is mainly that tackling that issue that deep learning models are currently very black boxes, not very trustworthy. There's a big crisis of trust in the technology world and for deep learning and AI in general also, especially as there's some questionable AI use cases, like in the judicial system in the United States and so on. And also, it's kind of interesting, but explainability is often tied to common sense too. If you actually ask somebody, why do you think this is a cat? They're like, well, it has eyes. And they're like, why do you think it's an eye? Well, like it's round, has a pupil. And like, why do you think it's a pupil? Well, it's like round and black. And it's like, why do you think something is round? And at some point, people are like, I don't know. It's just like people actually don't have access to visual cortex 1 and 2 neurons, right? It took researchers a long time to figure out that we have neurons that fire particularly when they see a certain edge. So, you can push all of these things a little bit to an extreme, but in general, for a lot of NLP tasks, there's a lot of common sense reasoning where that is very easily accessible. And so what we try to do here is essentially have deep learning models capture some kind of common sense. And so it's actually a very useful thing to know. And there are a couple of different data sets out there. For instance, there's some visual common sense reasoning tasks, like why is person 1 pointing a gun at person 2? In like, visual common sense reasoning, you have like contextual kind of common sense reasoning where you try to find like which ending would make more sense to a normal audience. And then here we have a common sense question answering where you essentially ask simple questions like, where would I not want a fox? A hen house, a bunch of chicken in England, in the mountains, in an English hunt, or in California. And for the most part, a fox would be really suboptimal next to a bunch of chicken because it'll eat the chicken. And so the correct answer here is hen house. But if you just try to do a classification problem here, like hen house is the only time that word came up. So you can't, it's not really the classification problem. And if you try to do old school NLP, where you try to logically create some knowledge base and then identify things, it would be incredibly hard to understand that, chicken are livestock, fox eat lots of other animals, and they would probably want to eat a chicken. And then if they're inside a building, then logically they're more likely to get to it. And it's impossible to write all of that down and then have an AI model try to reason about this very concretely and logically. And so we basically created a new data set of human common sense explanations and went ahead and asked people, okay, here's this question, where are trees safest? And this was the original common sense QA data set, but when we asked people to actually write out why they made a certain choice. Like state parks have rules to keep trees protected. And that's why trees are probably better off in a state park rather than inside San Francisco. And so by doing this, we actually realized that inside these human explanations, there are a lot of different kinds of world knowledge, right? There's cause and effect understanding, like disagreements lead to fights, or social norms, like forgiving activates good karma, or laws of physics, like gravity makes things fall. So there are a lot of different types of common sense reasoning and subtypes, and there's a lot of research on going even further, but these were some of the main groups that we found. And we released this data set, and I'll go into some more details, but if you're interested in any of this, it's all publicly available. The data set can be downloaded, and you can try to run your own experiments. And we essentially improved, just by including these explanations, we improved state of the art on this data set significantly. But then we went a step further and really wanted to use it also on unseen examples. And so what we did was essentially using the magic of language models that have been shown to do really, really well, give us better contextual vector representations, and so on. And we're basically including those and training and fine-tuning a language model that was pre-trained on a very large corpus. We fine-tune it to create these explanations given that context of a common sense question. So you have a prompt here, where a tree is safest, and then we rewrite in this text, the choices are University, State Park, San Francisco, and then we trigger the language model and write my common sense tells me, like literally those are the words that we trigger the language model with. Then we try to train the model to say, basically the right human explanation. State parks have rules to keep trees protected. So as we're training this, over time, the model gets better and better at generating common sense explanations for particular answer choices. And so at test time, of course, we don't have the ground truth. And so what we do after the model has been fine-tuned on common sense explanation training, we now ask it at test time to just generate that with the language model. And then we use that generated output of a language model as an additional input to a final answer prediction. So basically, what is happening here? The main idea is that language models, as they're trying to predict the next word, are actually implicitly capturing a lot of common sense. Like if you said, oh, he wanted to go to the store, so he got into his. Well, if it's a really good language model, you probably now know that that wasn't boat and it wasn't airplane, it was probably a car. Because most people don't, there's so many things that are going on just to predict correctly that he's probably getting into, and then the next word is car. And it's really hard to list all of those logically and exhaustively, but with enough statistics, you eventually get the idea. And so that's kind of the surprising insight of this, is that language models of just trying to predict the next word actually are starting to capture this really elusive goal of common sense knowledge, and then we can trigger these neural networks to do simple forms of common sense reasoning. It's a huge surprise, and I think we'll kind of sink into the world of AI slowly but surely. There are some really tough baselines where people took Google search queries and added a bunch of complex models, bidirectional attention, and so on, with Elmo and really good representation. So this was a really hard data set, and use all the knowledge that Google could give you and try to formulate queries and so on, and that gave you 47.7. Then OpenAI created a very large transformer, and that gave 54.8. And then human common sense explanation used during training only gave us 60, so not even using that same formalism at test time. But then, of course, in general, you always want to make your testing as similar as possible to your training without using the data. And so when we use this auto-generated language model explanations during training and at inference, we had a huge jump over 10% of the previous published state-of-the-art. And 10% increases in accuracy are not very common in the field of AI. That was kind of like close to what your first deep learning convolutional network they had over the previous traditional computer vision models on the ImageNet benchmark. So huge improvements. Those two numbers are coming from that paper, and this was the previously published state of the art. So almost 10% improvements over the state of the art. And also, still far away from humans, so still exciting research that can be done. And with that, I'm at the end of my time, and hopefully some more time for questions. Thank you.
So I think we have multiple different tasks. Do you think that single model will also be able to deal with different languages at the same time? Or do you think we will have to have different models for different languages? And I think I asked this for two reasons. The one reason is there is just way more English data, and you can train your language more than English and German. All your queries, I think, and all your tasks were all specified in English.
Right.
And German was the only thing that was able to output. Every time you add a language to that model, if you were going to say that one model to...
I don't want to claim I have the perfect answer and like I know it, because nobody has done it yet, and it's actually an active like research question. So I can only give you my hunch. My hunch is that for all Latin character family languages, we can probably in a not too distant future train a single model on all of it. Because you have A, B, C, D, E, maybe some accents and so on. And maybe some umlauts and stuff. And then if you can train on characters or character engrams, and you have some clever byte pair encodings of what character engrams those are, I think that will work. I think a lot of complexity, especially when you go to like Chinese characters, and then you went from like a few, maximum 100 characters that include digits and everything to like tens of thousands of useful characters. That's a very different formalism, and then all of a sudden, I think models would struggle to get with a single model to state-of-the-art numbers on everything. But I'm kind of optimistic. I think longer term, like it'll probably all be combinable, but it's a lot of complexity on the engineering side actually to then include, because if each models could be applied character by character yet, but computers will get faster over time and things like that, and then Chinese would add the complexity of like, well, now if you have tens of thousands of those and everything else is characters, so the models are really powerful and the vector representations for each character are really large to be able to do all the disambiguation, then Chinese would add extra complexity.
Seems like, maybe just a quick question. How much more computationally intensive is it to train a model for all of these different tasks at once than just fine-tuning for one task?
Great question. So question is how like computational costs. So of course, if you train on 10 tasks, you have at least 10 times the computational cost of training it. What's interesting, and this was part of the previous talk, it's actually less computational expensive to add an 11th task, because the model is already pretty good at a lot of stuff. And in some cases, you get it for free, like domain adaptation on different sentiment tasks. You don't even need to train at all. It'll just work. And then just fine-tuning on a domain adaptation on a similar kind of problem, you'll actually do better than if you just had the word vectors pre-trained, and now you have to train all the other weights of the rest of the model. So in that sense, computationally, once somebody has done it for you, it's faster. It's just like, it's really computationally expensive to even train GloVe or Word2Vec back in the day on the largest data sets, but once somebody's done it for you, it's a great resource, and now you can converge more quickly with pre-trained. So it's established that pre-training with word vectors makes models converge faster than not pre-training with word vectors, and they're more accurate. And I think we'll see something similar with pre-training the rest of the model. Great questions. Awesome. Thank you.